Swayam Prabha. Digital India. Educated India.
Maybe for the sake of recording, so just repeat just a couple of words that this virtual work is a very profound principle equivalent to Newton's laws or bodies under equilibrium, and Newton's laws can also be put as under dynamic equilibrium. And so in that context, we have virtual work. There are two terms here, virtual and work. So work, we just see how it is done because this is what we're going to use later. So work done by the force is F dot delta R, and work done by the moment is the one which is also important for us, is that the moment here can be replaced by two equal and opposite forces. And then the point AB here are going to take a new position here, which are at a distance of S, and then if A goes to A prime, B goes to B prime, and which can be construed of consisting of two components. So this AA prime and BB double prime is same, and BB double prime and B prime is along this line. So a little bit of discussion here. So if these two are equal, and if we know that this is a rigid connection, and for rigid connections, so that means that this A prime B double prime is also equal to A prime B prime. So this being rigid, so AB is equal to A prime B double prime as well as A prime B prime. So in this connection, then the total work can be really nicely written as F1 delta A product, and here F2 dot this delta B, which is here, can be summed up as delta B double prime and delta B double prime B prime. So this is how we write towards this end. And so what we know here is that since F2 is equal to minus F1, so the first term, this gets cancelled, right? Because delta A and delta B are same, and F2 is equal to minus F1. So we have the total work done will be that of F2 times dot okay. So if this is the case, so that means that there's an F2 here, and so the total work done is just equivalent to F2 taken a dot product with this one. So what happens is that when these terms are very, very small, and then we know that this distance is the same as this one. So we know that this is a kind of a chord, and in the limit, so this is perpendicular to, so in the limit, so this B prime, I don't even have to write this delta here. I don't have to write this one because, so as B double prime B prime is perpendicular to AB, as well as F is also perpendicular to AB, 2 is perpendicular to AB, as well as B double prime B prime is also perpendicular to AB, then what happens is that, so it is simply, so since these are in the same direction, okay, so in the limit what happens is that, so if that means that F2 and this one will be in the same direction, and then this is what's going to happen. Yeah, and so then we can write that it is simply F multiplied by the chord length here. So that means that delta U is simply, so it is simply F multiplied by this distance here, which is nothing but S into delta theta. So if this is delta theta here, so it is F2 into delta theta, which is simply equal to, so F into S is nothing but moment, and then it is simply M into delta theta. Okay, so this is the one which, so the work done by the moment is nothing but the moment and then how much it undergoes a rotation. So a moment is, it is just like putting a key, and then if you are turning it, then the work done by that moment is simply moment multiplied by the angular displacement. Okay, so this is, we require it sometimes, so that is why I wrote everything here for the sake of completeness. Okay, so these are the two terms, work done by the force, work done by the moment. So this is how we use. Okay, so now let's move on. Once we know this one, then we have another very important term, virtual. So this term virtual has two terms. One is virtual displacement, and force is not virtual, and then there is an associated term, work. So if the displacement is virtual, then the work anyway associated with that also is virtual work. Okay, so let's try to understand what is this displacement. What is that which we mean by displacement? So there are real displacements. So this is in contrast with real displacement. So how this is, how this virtual displacement and the real displacement, what is the change? What? Okay, so the change is that, let's look at this way. Say if you have particle here and particle under, so we have F1, 2, F3, and F4, and so on. So if this particle is under equilibrium, and then the particle, we are moving it. So this particle A is moved through a distance AA prime. So here AA prime is not real, in the sense that the particle is not actually moving to a new position. Okay, the particle is not actually moving. It's not moving. There's no motion. This is under equilibrium. Only for the sake of mathematical derivation, so we perturb it. So we do a hypothetical moment here. So AA prime is not real in the sense that the particle is not actually moving. Particle is not moving at all. It's under equilibrium. Okay, particle is not moving at all. But however, it's only a hypothetical. So it's only a hypothetical displacement or disturbance. Okay, so which we call as virtual. So it's only for the sake of whatever the derivation which we are going to do is that we are going to perturb it by a small distance here. It may be vectorial, so it is only hypothetical. So it's not actual real displacement. So to distinguish between the actual displacements and the virtual displacements is real displacements, which we put as real displacements. Usually we put it as dr, okay, and virtual displacement delta r. Okay, so that is the difference. So wherever you see delta r here, this kind of symbol, okay, this delta symbol, then we call it as virtual. And the dr, if it is actually taking place, then we call it as dr. We are going to put it later. Okay, so but however, both of them are very small. So both of them will satisfy the differential calculus. So both of them will follow the same differential calculus. Okay, so something like if there is an r square, so if you want to differentiate it, so then we call it as 2r dr. But in the case of the virtual displacements and what is the change in r square, we also call it as 2r delta r. Okay, so as far as the small changes are concerned, obviously it is also going to follow infinitesimal differential calculus formulae. Okay, so this is only for the sake of our mathematical derivation. We perturb it by a small. So for a particle, so what is it going to do? So for a particle here, if you want to move it through a small delta r here, so then here the work done, obviously, so each one of these forces are undergoing a displacement AR, and so that means that there is a total work done. So a total work done is total work done for this virtual displacement. So this we call as, say, Fi, or let me put it as F1. Here I'll put delta R, and F2, it is the same thing everywhere, and like this. So we have maybe, so this is the total work done for a virtual displacement. So such formula here is called virtual work. Okay, such formula is called virtual work. So that means that we are hypothetically moving point A to A prime. So F1 moves from here to here, F2 moves from this point to this point, and so on, F3 and F4. And each one of them is giving rise to a certain amount of work, and that work, you can add it, is called virtual work. So I hope you have understood. So this is not an actual work done. So in fact, this delta R is arbitrary. It's at our disposal. I can put it delta R like this one. I can put delta R like this one. I can put delta R in any other direction. But if you look at the real displacement, when you actually, a particle is acted upon by, say, unbalanced forces, so then it is going to go a real displacement. But here, we are not doing that real displacement. We are actually perturbing it for our mathematical evaluation of this principle. And so that way, we call this as virtual. So any work that's associated with virtual displacement is called virtual work. Okay. And virtual displacement is any hypothetical displacement of the particle or of a rigid body or even a system of connected bodies. Okay, so let us so now the is very interesting here. If you look at the virtual work for this one, what is that which we can do here? So the total work done here, delta R I can take common. So I can write this one as, so what is this one? So this is a very interesting, very simple formula. So I have sigma Fi times delta R. I took delta R out. So this is equal to 0. So this is because equilibrium. The particle is under equilibrium. So that is why. So sigma F is 0. So that means that the total work done is 0. So it's very, looks very simple. Sometimes you call it, sir, it's too trivial. What is so great in that? So what we are saying here, so that means that if a particle is under equilibrium, if you perturb it by a hypothetical displacement, which we call as virtual displacement, the work associated, the work done by all the forces for such a displacement is 0 because it is under equilibrium. Okay, so this is also true. That means that if a particle has virtual work associated with that is 0, so then the particle is under equilibrium. Okay, so these are equivalent. So there are a few qualifiers. I'm just going to go and tell them as we go along. And so what we have here is that for a particle, it's so simple. And so it is really not going to give you anything new tool. But however, let's just do it for the sake of, so how do we apply it to rigid body? So we know it can be applied to a particle here. And so if you have a rigid body here, so then how do I apply that? So I know very clearly that I can apply it to a particle. Okay, so this is the principle of virtual work. I will state it a little bit later. But however, the principle of virtual work says that if the virtual work or work done by any virtual displacement of a body under equilibrium, it will be 0. Or the other way, if the virtual work done by the particle for any virtual displacement is 0, so then the particle is under equilibrium. So this is a very profound statement. Okay, it's a very profound statement and very useful for us. Okay, so how do we apply it to the rigid body here? So how do we apply for rigid body? So since it can be applied to a particle, so the way of applying to a rigid body is that, so you will take the two particles here, say I and J, and if this can be applied to, say, ith particle, so for, if you look at ith particle is under equilibrium. So what we have here, so F1, F2, F3, and this is, so this is Fij. So this Fij, these are external forces, and while this is internal force. So this particle is under equilibrium under the action of all these forces. So we can definitely say that virtual work done by all the forces, okay, is 0 for this thing. So, but that will include this internal force also. This includes internal force. So what we are going to do is that how do we eliminate this internal force? Because we do not know internal forces. So, well, and then there are infinite number of particles. So how do we know all these internal forces? So how do we circumvent that? So for that, if you also look at the jth particle here, so jth particle has this internal force Fji together with some other forces here, F4 and F5 external force. So here also the work done by all the forces. So we have here, so this is a delta Ri for delta Rj displacement. So here total work done by the forces. So what is that? For here I think I should write what is the work done. So work done is associated with delta Ri, right? So I have here delta Rj. So for delta Rj is again 0 here, but this includes again work of internal force Fj. Can you tell me whether this Fij gets cancelled if I combine the total work done by the forces on the ith particle by the forces on the jth particle? So is the total work done by the internal force going to be 0? So however, we know that the internal forces are equal and opposite, but what about this delta Ri and delta Rj? So delta Ri and Rj, are they equal or equal and opposite, or are they equal? So delta Ri and delta Rj are not same. They're not same, right? Because if you look at I and j here and say so this, if you look at I and j particle, so there is an internal force Fi, j and Fji acting these particles, and then there is a displacement here for I going to I prime and j going to j prime delta Rj. So this Fij dot delta Ri plus Fji dot delta Rj, they're not equal and opposite. So of course we know that Fij and Fji are equal and opposite, but delta Ri and delta Rj are not exactly equal and opposite. So but however, for rigid connection, I and j distance remaining constant all the time because of the rigid body. So for rigid body, okay, we are only talking about for rigid body. So can we show that it is 0? So I'll give you a quick thing here. So just like we have done earlier, so j going to j prime, so let us divide it into, so a component j to j double prime, which is parallel to this one and equal, and j double prime to j prime, which is what is its characteristic? So which is perpendicular to the line ij or I prime j double prime. Both are parallel to each other. Okay. So if you look at the work done, so the work done by Fij for this portion, and let me write it here. Let me write it here. So this we will write it as J prime, so which is equal to delta Ri, and then there is something here, delta Rj, okay. So you understand it. So now this total displacement is written as delta Ri plus delta Rj prime. So this is equal to this one. So we can see very clearly that the first term here gets cancelled with this one, because Fij, Fji are equal and opposite. The delta Ri is the same. So this gets cancelled with this one, right? So that leaves what? Fji dot delta Rj prime. What do you think of this one? So what do you think of this term, Fji? So Fji, for as the particle moves along this displacement, okay, as this displacement. So how is this? How is this? So the force is like this, right, along this line, and as it moves through this distance here, as it moves through this displacement, force is, how is this force direction? The force direction is always perpendicular to the displacement. So the point is moving like this one, and the displacement is always perpendicular to the displacement direction. So obviously the work done by the force for a perpendicular displacement is Z, right? Because Fji and delta Rj prime, they are perpendicular to each other for a small displacement. Okay. So its dot product is 0. Okay. So like this. So what is that which we concluded? So what we concluded is that the work done by internal forces for a rigid body is 0. So that way, so if you combine the work done of this with this one, so here I said that it's including the internal force, but these two, when they are combined for a rigid body movement, it's going to be 0 and leaving only, so because of this, so work done by internal forces is 0. Okay, then that leaves, so that means that then the total virtual work done on rigid body for any, obviously, for any virtual displacement is equal to work done by external forces. Okay, so the work done by internal forces is equal to 0. So because of that, so what is that? The total work done by all the forces on the rigid body. So if you have a rigid body like this, so then, so all these internal forces gets cancelled as far as the work done is concerned. Then that leaves only the work done by the external forces. Okay, So this is a very important from the rigid body calculation. Okay, so this can be extended to a system of bodies. Bodies connected, and we come across many things like a crank and connecting rod, and say, let us say it has some weights, and then there is some force here. Okay, so this is under the action of this W1 and W2 and an action force F. This is under equilibrium, right? And then what are the other things? There are also other forces. So if you want to find out for a small virtual displacement, so a small virtual displacement in the sense that the new configuration for this one will be, let us say this is rotated by a small delta theta angle, and so here it's going to this piston is going to have a displacement here, so delta R, and this is going to have a small angular change. So this is a system of connected bodies. So it has so many internal forces as well. So not only the internal forces like this one. So if you look at the displacements, so if you apply it to each of these bodies, so for example, if you have, there are forces like this one, okay, and then there are forces. So let us say Bx, By. Okay, so this is A, B, B, and C. So if you, interestingly, if you draw the free body diagram of each of this is the crank with reactions here. And at B, if you separate out, then you have the forces Bx, By will appear, or internal forces will appear separately as external forces on each of these bodies. And then we have forces here. A normal reaction also will come into the picture. Okay. So interestingly, what you can also say here, that since these are internal forces, so when you combine the work done by all the forces, so the work done by these internal forces will again become zero. Why? Because this point B will undergo a certain displacement, but that displacement is the same either when you consider this crank or this connecting rod separately. Okay, so now if you look at this system of connected bodies, the work done by all the external forces is simply the work done by this weight, work done by this W2, and work done by this force. Another very important thing here is that the work done by the normal reaction here will turn out to be zero. So this is because in the principle of virtual work, we are going to say that the virtual work done by the system of external forces for a virtual displacement which is satisfying all the constraints. So here the constraint is that this piston is moving along the horizontal ground, right? If it is moving on the horizontal ground, then the normal reaction which is acting here will do no work. So the principle, if I enunciate, okay, we'll discuss this a little bit more in detail. So the principle is that the virtual work done by all the external forces, okay, on this mechanical system in equilibrium is zero for any and all virtual displacements which are satisfying all the constraints imposed on the system. Okay, so there are constraints, right? So there's this is supposed to rotate, cannot leave, and this is connected, and this is supposed to have a motion on the horizontal ground. So like this, so for a virtual displacement which is satisfying all the kinematic constraints, then the total virtual work done is zero for any virtual displacement. Okay, so this is a 1 degree of freedom of system, but then we also have systems with more degrees of freedom. So that means that we can arbitrarily take any number of virtual displacements. And so for all those virtual displacements, the total work done will be zero. Okay, so we'll continue this in our next class. So please try to understand this. This is a very profound principle and which is more powerful, okay, because many other forces here we need not take into consideration if they do not contribute any work, such as the normal forces, such as the internal forces, such as the reactions here. So all of them will not be accounted here because they will not contribute anything to the work. But however, if you just apply the equilibrium of each individual body, we have to take all the forces into consideration. So that way, this is much more profound and much more, many times is also useful.